Welcome to video 2 in the Marching Cubes and Minimal Surfaces tutorial. This video focuses on getting our base 14 meshes for our Marching Cubes lookup table. After we have these, we can rotate and mirror them in different ways to get all 256 possibilities. So we'll do all those transformations in the second part of this video. Before we jump back into the scripting component, let's do one thing to help us visualize what's going on. Let's color code the corners of the cube so that we know which corners are inside the volume and which corners are outside of the volume. So I'll need one more tree branch, and we want the same path, but it's coming from a different tree. This is our Boolean pattern, and let's pull our cube points over here and get a dots component. These will be our points. The size is way too big, so let's go slider between 0.001 and let's say 0.1. And let's make them a little bit bigger. That will do. I'm going to decrease the amplitude of this normal. So I'm going to get an amplitude component, and this is the vector. So let's multiply this by, that's good. Let's bring our dots down here, and we'll filter them based on the Boolean pattern. So this pattern already corresponds to the numbers of the point in this cube point list. So let's get our two colors first. Let's get a color swatch. Let's do, for blue we'll just, or for the zeros we'll just do a light blue, and for the solid let's do like a darker orange. We can merge these, and this will be our list. So we're either going to pick item 1 or item 2. This is our list of colors, and our tree branch or our Boolean pattern is going to be the list items. So it's either going to choose 0 or 1, and these are going to be our colors. And I'm going to hide everything else except for this. So I'll hide these. So now we just have our mesh, the normal, pointing towards the open space, which we've represented here with a blue dot, and all the solids are orange dots. The solid space are orange dots. And now we can jump back in and do the really tedious part. It doesn't have to be tedious if you don't want. If you just want to copy the code from pavilion.nuLUCA.com, this will be pretty fast and painless. If you're watching this on YouTube, just follow the link in the description to this page. Then just scroll down here and copy either one of these. This is all the code inside the scripting component, and this one here is just the meshes. So click copy, then just paste it inside your scripting component, and you're good to go. Remember, you'll still need the correct inputs and outputs. Also, if you do want to follow along as I type all of these out, you'll notice this is in Rhino 7. The code is just fine in Rhino 8 too, but I do make one change to make it a tiny bit shorter, and that change is reflected in the code that is shown later in this video. So if you want to skip to about the 8-minute 10-second mark, there the code is shown for all 14 meshes. Or again, you could just head over to the Pavilion website and you can copy and paste the C# script for the 14 meshes. Or if you're a member, you can just download the finished script. So I'll fast forward through this part, but I'll pause briefly to highlight the changes in at each step. So I'll basically be copying this part, and then I'll be changing what faces we add, and I'll be changing the Boolean pattern each time. So I'll highlight these changes each time, but since it'll be super boring to watch me type all this in, I'll fast forward. Okay, let's fly through this. Okay, so hopefully I did all of that right. We can check pretty easily by going through the branches here. That branch looks correct, so we're just going to check to make sure that the arrows are pointing towards the blue dots. Good. 3's good. 4's good. 5 and 6. And this is one of the more obvious ambiguous cases. The mesh you see here is assuming that the open space goes through the middle of this cube, but it could easily be the case that the solids are connected and solid is going through the middle. So in case you were curious about what an ambiguous case might look like, here's a good example. But again, we can fix errors that come out after the marching cubes algorithm runs. And I may do another tutorial that uses a version of marching cubes that addresses issues like this. Okay, so those all look good. And from these 14 different patterns, combined with the 2 null patterns, that's all 1s or all 0s, we can get to each of the 256 different possibilities just by rotating these meshes, rotating and mirroring. So we're just going to do some different transformations and combinations of transformations to these 14 meshes. We don't have to do anything to the null cases, of course. But it looks like all the mesh cases are correct. So before we go any further, I'll just put up on the screen the finished code for those 14 meshes. Here is the code for mesh 0 through mesh 6, the first 7 meshes, along with the creation of our 2 empty data trees, the M tree to hold our meshes and I tree to hold our Boolean patterns. And here are the last 7 meshes and their associated Boolean patterns, along with the 2 outputs, mesh tree and bool patterns. So our next step is just to create a big collection of transformations, a big list of transformations, and apply that entire list to all 14 meshes. So we have the meshes, they each have their own branch. So we'll get one list and run each branch through that list of transformations. Then we should have way more meshes than we actually need, but we'll organize them based on their Boolean patterns. So each will go into a branch that's designated by its Boolean pattern. So this one would be 0, 1, 1, 1, 1, 1, 1, 1, and this mesh would go into that branch. And by the end of this, we'll have multiple meshes in each branch. There will be 256 branches, and we just need to grab one from each branch because the multiples will be identical meshes. So let's start by thinking about what are the possible rotations and transformations that you can do to a cube so that it's still a cube with 8 vertices at these 8 points, but the vertices have switched positions. So we're just going to combine into a list every transformation that we can think of. So let's start by getting 3 planes. Let's get the XY plane, the YZ plane, and the XZ plane. And also the center point, the average of these 8 points. So first I'll get a mesh component, and let's hide that display in that wire. We'll call this mesh tree. Let's get an integer component. We'll call this bool tree, and we'll hide the wire. Let's just bring all of this over here. We need our cube points again. So this is going to be our most important component right now, this little point component that's holding all of our cube points, and we'll use these in a little bit. But for now, let's get our middle point. Oh, whoops. That is not the one that I want. I want our cube points, not our cube curves. So now we have our middle point, and from this we can get our axes. Let's get an XY. For our plane, let's get a YZ and an XZ. I'm going to hide all of these. So we can imagine rotating around 90 degrees, 180 degrees, and 270 degrees within each of these planes. So I'm actually going to get 4 different rotation components. Let's get degrees. In this first one, I'm just going to actually make a transformation matrix that is the identity matrix, just so we have the base cases. We have all 14 of our base cases. So I'm going to get a 0. And so really what we're doing here is just making a list of matrices that are what we're interested in is what's coming out of this transformation, this little X at the bottom. This is transformation data. And so if I get a matrix, we can get display matrix or transform matrix. I'll just get this. I plug this in. You can see that this is just the identity matrix. It's not going to do anything to a vector that you put in, to a point or whatever you put in there. It won't transform it at all. It'll give you the same thing out. So this will be our base case, and we're going to make a merge of all of these different transformations. This will be our first one. And then these next three, let's hide these since they're giving us this grid here. Just for the heck of it, let's put that in there. It doesn't matter. And these next three are going to be XY, YZ, and XZ planes, and we'll rotate those three angles I just mentioned, 90, 180, and 270. So I'm just going to type 90, and then let's go to multi-line data and type 180 and 270. Okay. So now what's coming out of, we don't need anything in the geometry, we just need that transformation matrix. And so we have three different transformations in each of these. It says rotate 90, 180, 270, and let's merge these three into our list of transformations. And next, let's think about it's one of those other axes that we can rotate along. So this we just rotated along axes that go straight through the middle. If the sides had center points, then one side through the far side. Next, let's do transformations around axes from corner point to the far corner point. So this one would go all the way over here, this one up here, this one down here. So first, let's just get those lines. So I can get a list item component, and let's get all 8 of our points. So we're going to I plus 7. And I'll need this again, so I'm just going to copy it and bring it down here. But let's work with this one now. I'll hide both of them. So there are 4 different lines that connect the far vertices. So let's get 4 line components. We have 0 connects with, this is 0, 1, 2, 3, 4, 5, 6. So it's going to be 5, nope, 6. And 1 connects with 0, 1, 2, 3, 4, 7. 2 connects with 4. We have 3 connects with 5. So that's our 4 lines. These are going to be our next axes of rotation. You can hide them for now. So let's do an experiment just to see what are the angles that these need to rotate at to get back to a cube that has all the points at the same coordinates. So let's get a slider between 0.000 and 360 and a rotate axis component. This is different than the last rotate component. We'll have this be the axis, and let's change this to degrees. And this time we will put geometry in so we can see how it's rotating. What's this default? Radians. Okay, so at 0, we can see obviously our points are at the correct spot or a correct orientation. And then if we rotate it around, eventually they get back. And so what is that angle? That's like 120. So if we type in 120, then that's one case that these rotate back on each other. And is there another one? Yes, this one, 240. And then 360 is just the same as 0. So we already have an identity matrix that rotates 0, but 120 and 240 are 2 different orientations. So if you look at like this point, for example, and then we rotate it to 240, now it's down here. Then we rotate to 120, now it's right here. So that's 3 different spots. This is at 0, 240, and 120. So we just need 2 different angles. We don't need this geometry plugged in anymore, but let's get 120 and 240. And since we have 4 different axes, we'll need 4 of these.
Plug these in. Then we can just merge these all here. Oops, I'm merging the wrong thing. I'll flatten this list. Now we have a list of 4 that we can plug into our larger list. So now we have 8 in there, or 18 since this is 1. Each of these is 3, so that's 9, 10 plus 8. Okay, I thought we were going to need this one, but we won't. Let's delete that. Then let's get our cube curves, because we already have this component. And this is going to be handy because our next axes that we're going to rotate around are going to come from the center points of these cube curves. So from this edge to this edge, the middle points, from this middle point down to this middle point, from this middle point up to here, here, over to here, and so forth. Those are going to give us some new axes to rotate around. And remember, I definitely want to err on the side of too many transformations because we want to make sure that we get every possible transformation in that tree, and then multiples are fine. We'll get rid of those later. So now let's just get the midpoints of all of these. I'm going to get a curved middle and a list item. Let's do, how many? We have 12, right? Yep. So list item, and we need to go to I plus 11. And let's start making these lines. So 0 to, I think this is, yeah, 0, that'll be 2. No, we don't want that one. So 0, 1, 2, 3, 4, 5, 6. Should have made these. Just make a bunch of them now. So 1 to 7 and 2 to 8. Or no, 2 to 4. And then we do have this one here, so that's going to be 0, 1, 2, 3 to 5, I think. Yep. Then we have this one across here. Then 9 to 11. I think we'll be fine with that. So we can hide all of these now. Also, we can hide these. Then we need 6 more rotate axis components. So let's get rotate axis. Change this to degrees. And these will be our axes. Pull all of this down just a little bit. And I think there's only one angle, and I think just 180 is the only time that the points match up again. So let's get just to check, 0 to 360 number slider, and let's rotate our cube points again. So if we watch from 0 back to when they come back into position, that is 180 degrees. And then we keep going. The next time is 360. So we just need one rotation, and that's going to be 180 for each of these. Disconnect this. And we can merge all of these. And all of these into our larger merge. Let's flatten it just in case. It should be fine. So we have all of those different rotations around every axis of symmetry, but there's one more thing we haven't considered, and that's mirroring. So let's just mirror this once and then do all of these rotations again. So let's compound transformations. First we'll do the mirror, and then we'll do all of these transformations again. So it doesn't matter how we mirror this, we'll just mirror it on the XY plane. We already have an XY plane, so I'm just going to get a plane component. And let's grab this, hide the wire. Let's get a mirror component. This is going to be the plane that we mirror it in. I'll hide this. And so we already have this transformation. It's scale 1D, so scale in one dimension, z -1. That's just flipping it across the XY plane. And let's duplicate, let's see how many we have in here. 24. Let's get a list length. First, let's graph this and let's simplify it. Then let's flatten this because we need this to match up with these. So list length is 24. Let's duplicate this mirror 24 times. So let's duplicate data. This is the data we want to duplicate. This is the number of times. Now we have 24 different 24 of the same transformation. We can merge this together. Merge, not mirror. So this will be our first transformation, but let's also graph and simplify this so that this looks the same as this up here. Good. And let's get a transform, or no, let's put this in. This will be our second transformation. And then we need a compound component. So this essentially compounds these two matrices into one, as if you were doing this transformation first and then this one. So now we should have 24 different matrices, 24 different transformations we do. And we can flatten this. So we have a list of 24. And let's get a transform. Nope. Just a component to hold this list of matrices that we started with. We can flatten that. So we have 24 here, 24 here. Let's merge these together. Now we have 48 different transformations, and we're going to run each of these 48 different transformations on each of our 14 different meshes. So we'll get more than enough as far as numbers go. We'll get more than 256 different meshes, but we should, once we organize it according to Boolean pattern, be able to weed out all of the duplicates. So I'm actually just going to apply this transformation to both our cube points and our mesh tree. So I'll bring the mesh tree over here and the cube points. And the reason we're doing both is because we want to check to see which points are equal to which. That way we know how to reorganize our Boolean patterns. So this part's a little confusing, but just because it's not super straightforward. But first let's make these transformations and then I'll try to explain it in a little more detail. So let's get two transform components, this one here. The first transformation will apply to all of the items in our tree. We can hide this. And the next one will just be to these 8 different cube points. So 48 transformations to these 8 different cube points. You can also hide this, but the cube points we need to graft. And we can simplify. So right now we have 48 points in each branch, so each transformation has its own branch. We want to flip that matrix so we have 8 points in each branch and 48 different transformations. So let's get a flip matrix. And then we're going to check which of these is equal. So which of the original cube points is equal to, get another cube point component. So which of these 8 is equal to these rotated ones. And that's going to give us a pattern through which we can shift around these Boolean patterns that were coming out of our first C# component. So we need to match these up with these according to how they rotated. And we're going to use another C# component to do that, and hopefully it will become a little more clear exactly what we're doing when we write that component.
And we will write the script for that component in the next video, so see you soon at that one.